Hey there everyone, let's look at this example. In this example there is a wire, a straight wire that is carrying a current that is equal to 0.13 amps, and there is a charge that is traveling parallel to that wire at 220 meters per second. This charge has a charge value of 6 microcoulomb, which is 6 times 10 to minus 6 coulomb. And because the charge is traveling near a wire that is carrying a current, the current creates a magnetic field around the wire. The charge then is traveling within the vicinity of a magnetic field. If there is a traveling charge, a moving charge within the vicinity of a magnetic field, it will feel a force of the magnetic field. We call it the magnetic field force. Now we need to find the value of this magnetic field force and the direction of that. Okay, so this is a good example because it involves many concepts. Okay, so we need to find the magnetic force. Okay, the magnetic force on a traveling charge, we know it is equal to Q as a value times the velocity of the charge times the magnetic field times sine theta, where theta is the angle between the direction of the velocity and the direction of the magnetic field. Let's see what we have. We need to find the force. We don't know what that is. We have the charge value 6 microcoulomb. We do have the velocity. We don't have the magnetic field. Okay, so we need to find this, the magnetic field. The magnetic field is created by the wire. Okay, that's good. And we have the distance at which we need to find the magnetic field at here. All right, we do have the current, and to find the magnetic field created by this long wire is, we know, mu naught I over 2 pi times the distance r. Okay, mu naught will be given and it's equal to Tesla meter per amp. Okay, all right, so the rest is known. So let's see, B is equal to mu naught is 4 pi times 10 to minus 7 multiplied by the current value, which is 0.13, divided by 2 pi. I'm going to leave that as it is now. And r is 3 centimeters, which is 0.03 meters. Now 2 pi with 4 pi remains 2. Okay, and doing this calculation we get the magnetic field to be equal to 8.67 times 10 to minus 7 Tesla. All right, good. So now we can plug it in here. FB is equal to Q, the charge 6 microcoulomb, 6 times 10 to minus 6 coulomb, multiply it by the velocity 220, multiplied by the magnetic field we just found, 8.67 times 10 to minus 7 times sine theta. Now what is theta? The theta, remember, is the angle between the magnetic field and the velocity. The velocity is easy, it's going up like this, but where is the magnetic field? Let's use the second right hand rule. Second right hand rule, we use this because the current now is going up. Grab on it so that the thumb is pointing to the where the current is going. Then the magnetic field to the right, where the charge is going in, and it makes a circle. So it's actually here, the magnetic field is going down perpendicular to the page. So it's perpendicular to the page like this, and the charge is going like that. If you look at this angle, you can see that the angle is 90 degrees. So that's sine 90, and sine 90 is 1. Doing this calculation, you can find out that the force of the magnetic field created by the wire on the charge is equal to 1.14 times 10 to minus 9 Newton. Okay, so now what's going to happen to the charge? Well, we want to know where the direction of that force. Now we use the first right hand rule. The charge is going up, okay, and the magnetic field is down, so the force is going to be towards the wire. So basically the magnetic force here is going to be like this. So what's going to happen to the charge? The charge is traveling at a high speed, and the force is bringing it towards like that. So the charge is going to do something like this. It's going to go around the wire like this, and getting closer to the wire, like as it's going up. Like it's going to go like this, like that, and it's going to get closer to the wire. Okay, and it's going to fall into the wire at the end, basically, very, very quickly. I hope this helps. Thank you very much.